In this video, we are going to look at more undecidable problems. In particular, we are going to look at undecidable problems from language theory. So in other words, the problems that we're going to look at are related to regular languages, context-free languages, and recursive languages, and so on. Okay, so first we are going to talk about a tool we're going to use to prove problems that are not decidable. So this tool is called reductions. So let's look at what it means by a reduction. So we have, let's say we have a language A, okay, and then we say that we can reduce this language A to a different language B. So B is a language by a Turing machine M. Okay, what it means here is that that we have, okay, X is in A if and only if M, this Turing machine M on this input X produces a string, let's say Y, okay, and that's in B. So here we are thinking of this Turing machine M as a function. So in other words, M computes a function. Okay, so this is M of X that gives the output Y. If this is the case, then we say that A is reducible to B. Okay, so this would be a period. So then we have the following theorem that says this: if A is reducible to B and A is undecidable, then neither is B. Okay, hence we can, if we know a undecidable problem, and we can reduce this problem A, which we know is undecidable, to a new problem B, then we also know that B is undecidable. Hence, this reduction is really a tool for us to prove a new language that is not decidable. Okay, so this theorem is pretty straightforward. Well, the proof is pretty straightforward. Okay, so let's see the proof. Suppose that B were decidable. Okay, then it means that there is a decider, D sub B, that always holds, and Y is in B if and only if D sub B accepts Y. Okay, so it always holds, and that means that we talked about this earlier. It always holds. When it holds, it will either end up with an accept state or a reject state. And an accept state means X is in A, and the reject state, sorry, the accept state means that Y, okay, we're talking about Y here, Y is in B, and the reject state means that Y is not in B. Okay, so that's what this decider means. Now, since A is, by assumption, reducible to B, that means that there is a Turing machine M such that X is in A if and only if M of X is in B. Now remember, this M of X produces an output Y, okay, on any X. It always halts and it produces an output y. So now, based on db and this m, we are going to construct a decider d sub a for a as follows. So it takes input x, and then it runs m on x. Okay, so this is what this d sub a does. So for any input, so for any string x, it runs m on x. Okay. Okay, so then run db on m of x. Okay, because this m produces a y. So then I want to use db to determine whether this y. So you think of this as a y, whether y whether db accepts y or not. Okay. So that's what this construction, that's what this dA does. So let me write it here. So what dA does is on input x, run m of x, that's equal to y, then run db on y. Okay, because this m always halts and produces y, and db always halts, so dA always halts on this input x. And it accepts x because, so this means that if db accepts y, then it accepts x. If db rejects y, then it rejects x. Okay, so that really means this, that it accepts x if, so dA accepts x if and only if db accepts y. What it really means that if and only if y is in B. So if and only if y is in B, and then by the reduction, we also know that if and only if x is in A. So that means that this dA decides A. Okay, so that is the proof. Okay, so now we know that Turing, we also know that Turing acceptance problem, A sub Tm is undecidable. So then to show that a different problem, L, is undecidable, what we are going to do is to start from A sub Tm. So we're going to reduce A sub Tm to a language L. So we use this less than or equal to mean reduction. Okay, so that means ATM is reducible to L, then L is not decidable. Okay. So now let's look at Turing halting problem. So the halting problem takes an encoding of a Turing machine M, comma X as input. M is a Turing machine, and M halts on input X, okay, instead of accepting X. So in your homework, you are asked to prove this Turing machine halting problem, H, in your homework we call it H, is undecidable using diagonalization directly. Okay, so you can, of course, we can prove, we can show that, we can show it is undecidable using diagonalization. But now we're going to reduce A to M to halt Tm, A sub Tm to halt sub Tm. So then we know, because A sub Tm is not decidable, as we proved last time using diagonalization, then we know that halt sub Tm is also not decidable. So the proof is just to construct a reduction. So what we're going to do here is that we're going to construct a reduction. So that reduction is a Turing machine M sub H that takes an encoding of a Turing machine and input X as input, and it outputs a encoding of a new Turing machine M prime and input X. And in this M prime on input X halts if M accepts X. Okay, so in other words, M prime computes, well, so M prime is a simulates, so M prime on X simulates M on X, because that would be the following outcomes. So either halts, either accepts, okay. If it's accept, then M prime will simply halt, or M on X either reject or infinite loop, or loop. Okay, so if that's the case, M prime halts, and then in this case, M prime loop. Okay. So that's what this M prime does. So this is a reduction. And now we know. Now we show that why this Turing machine MH, right? So MH that takes this input, think of it as an integer, and outputs another integer M prime X. So now we know that M prime X is in A sub Tm if and only if M prime X. So if it accepts, it halts. If it doesn't accept or infinite, then it's not going to halt because it's going to loop. So that means that it is halt sub Tm. So this is the easiest reduction. That this is the easiest reduction. Okay. So for the other undecidable problems, a reduction may be more difficult, but we just want to demonstrate using this simple example the idea of constructing a reduction. Okay, so this is a theorem we looked at last time. So a language L is decidable if and only if its complement L bar is a language L is decidable if and only if L bar is decidable. Okay, because decidable means that it's a decider that always holds. So you just need a switch accept state with reject state. Okay, you just swap them. Then that the new decider by swapping accept state with reject state accepts L bar, decides L bar. So now we're going to look at a new undecidable problem. So that's called NE sub TM. Here we only take an encoding of a Turing machine as input. Okay, then we want to know whether this M accepts something, right? So in other words, the language accepted by M is not empty, it accepts some string. So in other words, you are given a Turing machine and you want to know whether the Turing machine actually accepts something is not decidable. Intuitively, it means that you just enumerate all possible inputs, okay? Then you keep running it. You keep running it, so you can do it concurrently, right? So you enumerate x1. Now intuition is like this, and then I'm going to so for any m, I enumerate this. Okay, so we can do it using lexicographical order, and then we're going to run m on x1, m on x2, and so on concurrently, right? So you run this, you run m on x1 for one step, and then you run m on x1 on one more step, and this time you start running m on x2 for one step, and so on. So if one of them halts, you halt, otherwise you just keep running. Okay, so but if m doesn't accept any input, it will just keep running. Okay, so that you will not know. So that's not, so in other words, it may not hold. So that's why it's not decidable. Now that's intuition, so you cannot use that as a proof. So to prove it formally, we are going to reduce A sub Tm to Ne sub Tm as follows. So what we do is we construct a Turing machine that on input m comma x, because that is the input to A sub Tm. So what it does is to output a new Turing machine, m sub x. Okay, so this is, so in other words, my reduction takes encoding of m comma x as the input, and it produces a output m sub x, so which encoding of m sub x, so which is a Turing machine. And what it does is that it takes input w, and then you check to see whether w is not equal to x, right? So this m sub x takes input w, okay? And then you will have two cases, whether either w is not equal to x or w is equal to x, okay? Because you know this m, you know this x, so then of course, based on m and x, I produce a new Turing machine that on input w, if w is not equal to x, then reject. So M prime reject. Okay. And if W is equal to X, then simulate or run M on X. Okay, so this is what this MS does. So now let's see what happens. So if M comma X, the encoding of M comma X is in A sub TM, so that means M accepts X. Okay, so this means M accepts X. So when M accepts X, that means that it will accept when it will accept this X. So that means M on X, on input X, accepts it. Okay, so it means that X accepts X. Because when the W is equal to X, you run M on X. So it accepts it, so that means that L is not empty string because it does accept X. So likewise, if M, the encoding of M sub comma X is not in A sub TM, so that means that is M rejects X. Okay, then so let me write it here. So if, so let me do it here. So if M sub the encoding of M comma X is not in A sub TM, so that means that M doesn't accept X. Okay, it could be it could be two cases. One, it rejects X, other, it goes to infinite loop. So in this case, we're going to see for MX. Okay, so of course we know that when W is not X, it rejects. So we know that MX rejects every input that's not equal to X. And for input X, when W is equal to X, okay, then we know that and MX doesn't accept X. So meaning it will either go to infinite loop or it reject X. So nevertheless, so it really means that MX doesn't accept X. So that means that it implies that, so let me put it here, that, so this implies that the encoding MX is not in L of M, because L of M means, sorry, we should say that it's not empty. It is empty. Just put it in here. Oops. For some reason, I cannot remove it. It's a weird thing. Looks like I have a system issue here. Okay, it's back. I had internet issues that disconnected me. So now this implies L of mx is empty. It's empty set. So that means that the encoding of mx is not in NE sub Tm. So this NE means non-empty. Okay, so then we know that the ME sub Tm is not decidable, so its complements. So this is it's a complement. ETM is just a complement. So it says it's not empty, that means it's empty. So that means ETM is not decidable either because NE sub Tm is not decidable. Its complement is not decidable either. So that means that E sub Tm is not decidable. Okay, so next we're going to see a undecidable language that's related to regular languages. Okay, so we call it regular sub Tm. So this is similar to A sub Tm, but here we want to know, or this, that L of M is a regular language. Okay, so remember when we look at E sub Tm, not A sub Tm, so we look at E sub Tm. So it is just a encoding of a Turing machine where L of M, the language accepted by M, is empty. So we know empty set is irregular, so we generalize this a little bit. So then we are going to put regular. So this is really should be just the encoding of M. Okay, so we just want to know whether this Turing machine M accepts a regular language. So it is a natural generalization of E sub Tm because we know that the empty set is always regular. So we replace empty set to regular. And then this language is undecidable. So again, we're going to reduce A sub Tm to regular sub Tm to establish its undecidability. So first, we know that the full set, sigma star, is irregular. And so we call it L1, and then L2, which is a set of 0 to the n followed by 1 to the n, or in the n, is not regular. So we can prove it easily using an infinite Fooling set, which is a 0 star. Okay. So now that means that we're going to construct a Turing machine that on input M, this is encoding M comma X, which is we think of as A sub Tm's input. It produces a Turing machine, let's call it M sub X, as follows. So on input W, okay, And then we first check to see whether W is in the form of 0n followed by 1 to the n. Earlier, when we look at n sub tm, so on any W, we want to know whether it is equal to W. So in this case, we just want to see whether W is in this form. Okay. And if it is in this form, m sub x accepts. Okay, otherwise, m sub x runs m on x and accepts W if m accepts x. Now, this looks a little bit, it may look confusing. So let's draw up something here. So we have an input m comma x. Okay, so mx, based on this input, one is m, the other one is x. So this is my Turing machine m sub x. Its input is w. Okay, so then if w is in the form, this mx accepts w. Accept. Otherwise, if it's not in this form, simply simulate m on x. So simply run simply m on x. Okay. So now let's see whether this is a reduction we are looking for. So, so by this construction, we know that if m does not accept x, okay, so so we go back to the construction of the last step. So if m, so if w is not in 0, if in here, we run m on x and accept w. So if m accepts x. Okay, so let me finish up here. And accept w if n accepts x. Okay. So now, if m does not accept x, then it means that if m does not accept x, what does that mean? It means, okay, so now remember this mx always accepts input in the form of 0 to the n followed by 1 to the n. So this is always accepts it. So if m doesn't accept x, then mx does not accept anything else. So that means that mx accepts L2. Okay, then we know it is not regular. If m accepts x, now remember this mx always accepts this. So if m accepts x, then m accepts any w. Okay, so that means that this mx this mx accepts sigma star when m accepts x, which we know that sigma star is regular. So that means that the encoding m sub comma x, which is in A sub tm, which means that m accepts x, if and only if the encoding of this Turing machine m sub x is in regular sub tm. Okay, so hence we established the fact that regular sub tm is undecidable. So So in other words, given the Turing machine, we want to know whether that Turing machine accepts a regular language. It's not decidable. There is no algorithm that you can follow that algorithm step by step, and eventually you get an answer. So in other words, you won't. So there isn't any such thing. Okay, so it's not decidable. So similarly, we're going to look at EQ sub TM. So EQ means equal. So you're given an encoding of two Turing machines, M sub 1 and M sub 2. You want to know whether M sub 1 and M sub 2 accept the same language. And this is not decidable. Okay. So so for this problem, we're going to reduce E sub Tm to EQ sub Tm. Because earlier we showed that E sub Tm is undecidable. So if we can reduce E sub Tm to EQ sub Tm, then we know EQ sub Tm is not decidable. Okay, so here is the reduction. So we let M sub E be a Turing machine such that it accepts nothing. Okay, so this is, so in other words, it rejects every input. So it accepts nothing. So the language accepted by M sub E is empty. So now we construct a Turing machine M sub EQ, and that is a reduction as follows. So the input of E sub Tm is an encoding of a machine, single machine, and the input of EQ sub Tm is an encoding of two Turing machines. So that means on this, we're going to generate the encoding of two Turing machines. So what we're going to do here is on input M, this Turing machine M sub EQ, which is a reduction, outputs two Turing machines. One is a Turing machine M sub E, which rejects everything. The other one is just M. Okay. Then L of M is equal to empty set. Okay, because now we reduce this. So this M, the encoding of M is in E sub Tm, means that L of M rejects everything. So that means because we know that ME also rejects everything. So if M rejects everything, then L of ME is not equal. I'm sorry, is equal to L of M. And then likewise, if M accepts something, then they are not equal. Okay, because so if L of M accepts something, then L of ME cannot be equal to L of M because L of ME is empty. Okay, so that establishes the reduction. Okay, so so much for now. Let's take a short break, and then we'll come back to look at more undecidable problems. So let's pause a little bit and let the ideas sink into our head. So we have looked at several undecidable problems and how we prove their undecidability. So so this is time to pause and think about the proofs. And for a little while, then we'll come back. Okay, so then Then we'll start the next video.